from the initial state. And this is a work that I have done together with Nestor Armesto from Santiago de Compostela and our common PhD student, Pedro Agostini, who just finished his PhD last month. So the paper is, I gave the archive number, but okay, this is already published, so I just put it there, the archive number just to make it convenient for everyone who would like to go and look for details. Okay, oops. So, okay, here is the outline of my talk. So since I didn't know the audience, and I don't know whether, okay, you're familiar with the color glass condensate or CGC or small X physics, I decided to prepare like a little introduction to small X physics and CGC. So I'll first discuss about the basics of this effective field theory, what's called as like color glass condensate, and then I will go ahead and start talking about like multi-particle correlations and how we can do this calculation in the CGC framework. So this is going to be a general framework to compute any number of gluons, but then, okay, of course, I'm going to focus on the 2-particle and 4-particle correlations, and I will give the results and discuss the results for those two. And then I will finally end up with some discussions, outlook, and also some criticism for what we have done. But okay, by the way, please feel free to interrupt me anytime if there is any questions during the talk. We don't have to wait until the end. Okay, so let me start with the very basics. So in high energy scattering in QCD, we have like two different regimes, hard scattering and soft scattering. In the case of hard scattering, in the hard regime, we have a large momentum exchange between the projectile and the target during the interaction. And in this case, in this regime, the theory is weakly coupled, and we can use perturbative methods in order to study this regime. On the other hand, we also have soft regime or soft scattering. In this case, the momentum exchange between the projectile and the target during the interaction is small. The theory is strongly coupled in the regime, and we need some non-perturbative tools in order to study this part. On the other hand, we know that deep inelastic scattering is a very useful observable that we can learn a lot from in QCD. And in DIS, we have an incoming electron with momentum k, which emits a virtual photon with momentum q. And this virtual photon scatters off the proton by interacting with a quark with momentum p and the outgoing quark as momentum p plus q. So in this process, we have three Lorentz invariant quantities. One of them is the virtuality of the incoming photon, which is this q squared. The other one is the longitudinal momentum fraction carried by the parton. In this case, it's the quark. And the third one is the energy of the colliding gamma p system, which we can write it as 2p dot q. So all of these three Lorentz invariant quantities, two of them are independent, and the third one is dependent on the first two. So the independent ones are the virtuality of the incoming photon and the longitudinal momentum fraction. And we can actually write down the energy of the colliding gamma p system in terms of these two quantities, where it can be written as q squared over x. So if I want to increase the energy of my system, now I have two different choices. I can either go to the Bergen limit, which basically means that, okay, I fix the values of x and I increase the value of q squared. Or I can go to the Regge-Gribov limit. So it basically means that, okay, for the fixed values of q squared, I simply decrease the value of the longitudinal momentum fraction carried by the parton x. So even though both of them increases the energy of the colliding system, but they probe like completely different physics. In the Bergen limit, when we fix x and when we increase the q squared, the density of the partons decreases, system becomes more dilute as I increase the energy, and the evolution in this case is given by the Diglap evolution equations. On the other hand, in the Regge-Gribov limits, when we start decreasing the values of x, for fixed values of Q squared, the density of the partons increases, system becomes dense, and during this X evolution, the emitted partons start interacting with each other, which causes the saturation. So first, just to be like completely covering everything, even though it's not going to be detailed, let's start with the Bergen limit. Even though I'm not going to talk about this, it's not going to be part of my talk, but let's just start with it. So in the Bergen limit, the description is given by the QCD improved parton model. And in this case, proton is seen as a set of independent free partons, and it's assumed to be dilute. And in that case, we can write the gamma p cross-section in the collinear factorization as a convolution of perturbatively calculable coefficient function, the C, and parton distribution function, which is written here as F. So these PDFs are the number density of partons of type, some specific type, let's say type I here, in the proton, which is seen with the transverse resolution 1 over Q squared, and they're carrying a momentum fraction Z. In the infinite momentum frame, the transverse size of the photon is very small. It's like 1 over Q. And it can only scatter off a quark with roughly the same size of itself, which is, again, 1 over Q. So in this sense, we can think of Q as the transverse resolution scale. So if we increase Q squared, then we will be able to resolve more substructure. So what was seen as like a single parton will be seen as like two smaller partons that we will see in the transverse plane. So in other words, target effectively contains more partons during this after this Diglep evolution or increasing Q squared. However, the density of the partons decreases. And this evolution, as I was saying, is given by the famous Diglep evolution equation. It basically tells us how the PDF's parton distribution function changes with respect to log of Q squared, and it's given again in terms of the parton distribution functions with also splitting functions. On the other hand, which is what I'm more interested in, is so-called Regge-Gribov limit, which corresponds to decreasing the value of X at fixed value of Q squared. So this is the first approach to this limit was given by the famous BFKL evolution equation. So it was done by Balitsky, Fadin, Krylev, and Lipatov in 77 and 78. And this BFKL evolution equation tells us how the unintegrated gluon density changes with rapidity. Rapidity is defined as log 1 over X, and the unintegrated gluon density is related to the PDFs through this relation. So we just integrate over the transverse momenta of the unintegrated gluon density to get to the PDFs, the certain PDF. So BFKL evolution equation tells us how the unintegrated gluon density changes with increasing rapidity. The BFKL equation was a great success in the studies of the high energy scattering processes. It gave a lot of insight to both theoretical and experimental works. However, it was also realized that like at very high energies, BFKL equation suffers from two major problems. So the first one is the Froissart bound. The cross section that is calculated by the solution of the BFKL equation behaves as exponential of the rapidity. But the Froissart bound tells us that like the total cross section should be less than square of the rapidity. So this is a problem of the BFKL equation. But in order to solve this problem, one needs information from the infrared scale of the QCD. The other problem is the violation of unitarity. In other words, the scattering probability grows without a bound, and it exceeds unity at rapidities of order 1 over alpha s log 1 over alpha s. This is through the BFKL equation. And this is also a problem, but this problem can be addressed by taking into account the gluon saturation effects, which is going to be the main topic in my talk. So if I go to the Regge-Gribov limit, so if I decrease the value of X for fixed Q squared, which corresponds to the rapidity evolution, then what we can see here in this cartoon is that with the increasing energy, the number of partons increase due to splitting. However, since we're not changing the transfer scale, Q square, the mother and the daughter partons will have the same transfer size, and the density of the partons will increase until they start interacting with each other, and then at that point it will cause the saturation phenomenon.
Tolga,
yeah.
Before you go on this slide, could you go back and so you mentioned the DGLAP evolution, and I was curious if this listed problems has some equivalent in the DGLAP case. For example, in the DGLAP case, there are also large logarithms, but those logarithms looks in a different way.
Yeah, but okay, the problem of large logs in DGLAP is somehow different from the problems that we have here. So the problems that we have here, like the problem with the BFKL, is more fundamental. So, for example, okay, violation of unitarity is a big problem of BFKL. But then, okay, we don't see this kind of problem in the case of DGLAP. So, in other words, like DGLAP and BFKL, okay, Bergen limit and Regge-Gribov limit, even though they're both increasing the energy of the system, they're completely probing different physics, and they're suffering from completely different problems, their own problems. Okay. Okay, so then, okay, so this is a very well-known cartoon in CGC that basically summarizes what I have been saying. So, in order to increase the energy of my system, I can basically either go to the Bergen limit, which means that okay, for fixed values of x, for fixed values of x, I increase the value of q squared. So I go from here to here. I end up with a dilute system than the one that I started. This evolution is given by the DGLAP evolution equations. In the case of Regge-Gribov limit, for fixed values of q squared, I start decreasing the value of x, which means that I go in this direction. And okay, I increase the density of my initial profile, if you wish, and up to a point where they start interacting with each other. So this is what we call as the saturation, where it starts interacting with each other, and it's defined in terms of the saturation scale or saturation momentum QS. Roughly, this is like alpha S times gluon density per unit area, and it's a measure of the strength of gluon interaction processes that may occur when the gluon density becomes large. After this point, so BFKL equation is a linear evolution equation. After this point, there's also nonlinear generalization of the BFKL equation, that's known as like G-Walk or BK evolution, which I'm going to talk about it in a second. So the nice thing about this is that, okay, like QS is still much smaller than lambda QCD, which means, okay, it's weak coupling, and we can still use perturbative methods to study this. So Larry and Raju in '93, they basically give the prescription of scattering processes in the saturation regime in terms of so-called color glass condensate or CGC effective theory. CGC describes a process in terms of the effective degrees of freedom with respect to a cutoff lambda plus. So fast partons inside the system whose longitudinal momenta is larger than this cutoff are described by the color sources. So it's called with J nu, for example. And the slow partons whose longitudinal momenta is smaller than this cutoff are described by the color fields A mu. The interaction between the fast and slow partons are given by this guy here. Then, okay, like within the CGC framework, we need to, okay, like the important thing is, okay, how we calculate the expectation value of an observable. So the expectation value of an observable is computed by introducing the distribution function of the color sources rho. So basically you take your observable, you multiply it with your distribution function, and everything is a functional of these color sources rho, and then you integrate over with this distribution function. So this nonlinear generalization of the BFKL equation was given by Jim Walk. It is generally in Marian, Yankel, McLaren, Weigert, Leinero, and Kohner. And it basically tells us the rapidity evolution of a distribution function, how it changes with rapidity. Here, H is the Jim Walk Hamiltonian. I didn't write the explicit expression for this Jim Walk Hamiltonian, but it's a function of rho and d by d rho. So it's a functional equation. And in this case, in this limit, no matter what, the interaction between the projectile and the target are given in the eikenl approximation. This corresponds to the case where each parton is picking up a Wilson line during the interaction with the target. So if it is a quark, I have a fundamental Wilson line, and this Wilson line is a path-ordered exponential of the background field of A minus. What appears in the observable is, because like this is the Wilson lines that appear they're appearing at the amplitude level, but what appears in the observable is dipole operators or quadrupole operators, which are trace of UU dagger for the case of dipole, or trace of UU dagger for the quadrupole. And this normalization dr is the color dimension of the representation. So if it is fundamental, it's 1 over nc. If it's adjoint, if it is a gluon that's scattering, then it's 1 over nc squared minus 1. Well, okay, I didn't write down the explicit expression for the Jim Walk Hamiltonian, but I would like to tell, okay, a little bit about like the Jim Walk equation for the dipole operator, how the dipole operator changes with rapidity. And this has, as you see, two different terms. If you calculate it, okay, we have two different terms. One is the same dipole that scatters, that goes through the scattering, and it doesn't evolve with the rapidity. But then there is another one, which is this double dipole operator that sits at the same, okay, that shares one transverse position of both of the dipoles. So in principle, this dipole operator or dipole scattering probability can be written in terms of the scattering probability n. And if this double dipole operator basically corresponds to simultaneous scattering of both dipoles through the target. So in 96 and Balitsky, and then in 99 Yuri, they show that, okay, like by assuming the area of the target on which the dipoles are uncorrelated, they show that they can write down this double dipole operator as expectation value of single dipoles. And in this case, they go from the Jim Walk equation to well-known BK equation. So I've said all these things just to give the idea of what is CGC and what is nonlinear evolution, what is saturation. But most importantly, I would like to discuss about the possible applications of this gluon saturation regime. So we have different cases. So for example, if I look at dilute scattering, it means that, okay, there's no saturation effects neither on the projectile nor on the target. And in this case, I can use the BFKL formalism, and it can be applied to gamma star, or DIS on a proton, or proton at moderate energies. Then, okay, we also have dilute dense scattering, and in this case, we have the dilute projectile, but our target is dense, so we will have saturation effects on the target. In this case, we can use the CGC formalism, and it can be applied to DIS on nucleus or proton-nucleus collisions or forward particle production in PP. There is also dense scattering, which you guys are much more expert than me. So in this case, both the projectile and the target are saturated, and for that one, CGC formalism is not enough. So one has to use the nonlinear dynamics of Young-Mills fields, and this can be applied to PP at very high energies or heavy ion collisions. So in the rest of the talk, of course, I would like to stick to the CGC formalism, and I would like to understand the dilute dense scattering or PA collisions. And there are different saturation sensitive observables in PA collisions. For example, okay, you can look at forward particle production, forward jet production, correlations in forward production. But there's also a saturation sensitive observable that's mostly used to test saturation effects is two particle production at mid-rapidity or multi-particle production at mid-rapidity, and the correlations related with these particles that are produced at mid-rapidity. So I will be mostly focusing on this. So let me first start with the two particle correlations. Why we get excited. So basically, our motivation is the ridge structure. So on the right hand side, you can see the plots from Atlas, PP at 13 and 5 TeV, and then PLED for 5 TeV, with minimum bias events on the left and then high multiplicity events on the right. What we basically realize here, and so this is like the correlation function that's plotted as a function of the azimuthal angle and the rapidity, relative azimuthal angle and the rapidity. What we basically see here is that, okay, for PP and PLED, which are small size systems, for high multiplicity events, we see like this ridge structure. So there is a correlation between the particles over large intervals of rapidity, peaking at 0 and pi, relative azimuthal angle, and it expands large values of rapidity, delta eta. So this was first observed at RIC in gold-gold collisions, and then it was also observed at LHC for high multiplicity PP and PA collisions. When it was observed at RIC for heavy ion collisions, or RICH that we observe in heavy ion collisions, it is a well-accepted and established explanation. It is collective flow due to strong final state interactions. And there is a good description of the data that's given in the framework of relativistic viscous hydrodynamics. However, seeing RICH in small size system, like PP and PA collisions, it kind of feels like, okay, similar reasoning looks a bit tenuous. But I also have to say that, okay, Hydro again describes the data for the small size systems very well. But this actually, like seeing this RICH in small size systems triggered a lot of discussions in the CGC community, and we basically started asking the question whether, okay, what the correlations that we see in small size systems, can it be the initial state effect? And the idea behind this is that, okay, the final state particles carry the imprint of the partonic correlations that already exist in the initial state. There were several mechanisms that has been suggested to explain these rich correlations in the CGC framework. One of them is so-called local anisotropy of the target fields, or the domain model of the target, which was introduced by Alex and Misha in these three papers, and then the numerical studies of this model or of this mechanism was done by Adrian and Vladi, and then Adrian, Vladi, and Larry in these two papers. So the idea here is very simple. Basically, you say that, okay, my target, my dense target, is composed of domains of chromoelectric fields. In each domain, my fields, chromoelectric fields, the strength of it and the direction of it is different from the other domain. And these domains are has the size of roughly like 1/QS. So the physics behind the way that it works in this case is actually very simple. So if you have two particles that are already correlated in the incoming wave function before it interacts with the target, it means that, okay, they're basically sitting close to each other in the transverse plane in this incoming wave function. So the transverse separation is much smaller than 1/QS. So it means that, okay, when they scatter, when they interact with the target, they actually scatter through the same domain. So it means that, okay, like the strength of the strength that they feel and the direction of the field is exactly the same. So whatever was in the initial state actually transfers to the final state. So if they're correlated in the initial state, then they will be also correlated in the final state. The other very famous mechanism is the so-called plasma-graph approach to gluon production. And this approach was introduced by these gentlemen in these two different papers. And let me basically explain you what it is. So what you see here is a cartoon of the square of the scattering amplitude. So on the left hand side, I have the of the dashed line, I have the amplitude, and on the right-hand side, I have the complex conjugate amplitude. I have two colored charges that are in my projectile, and each of them are producing a gluon, are emitting a gluon, let's say K1 and K2, and then they interact with the target, and the momentum transfer from the target is Q1, Q2. The initial momentum in the projectile function is wave function is K minus Q and K1 minus Q1, and the outgoing guys, the tagged gluons are K1 and K2. So this also was very popular, and they were able to explain many aspects of the data, but it was not very clear what is the physics behind this plasma graph approximation. So in a series of papers together with my collaborators, we have shown that, okay, like the plasma graph calculations contain two different physical effects. One of them is so-called Bose enhancement of the gluons, either in the projectile or in the target wave function. So in this case, the correlations, okay, like the correlations that we observe are apparent either if it is like the Bose enhancement of the projectile, then it is when the momenta of the gluons in the projectile wave function are the same or opposite. If it is the target, it's the same with the momentum transfer from the target. And there is also HBT correlations between the gluons that are produced. And these guys are either, okay, we see them either when they are equal to each other or opposite for the momentum of the produced gluons. Okay, plasma graph calculations are very nice, but it was only valid for dilute scattering. In other words, it was valid for PP, and we wanted to go beyond this, and we wanted to understand this approach for the case of PA. And again, with my collaborators, okay, we were trying to extend this to the gluon production. And in this case, the difference is that, okay, you get like scattering on a because you are scattering on a dense target, you get dipole and quadrupole operators. In this case, we were using a factorization assumption where we were writing the quadrupole or the double dipole operators, target average quadrupole or double dipole operators in terms of single dipole operators. I will come to this and I will explain you, okay, this is what we call as the area enhancement argument. I will come back to it and I will discuss it in more detail in a couple of slides later. But what I would like to say here is that, okay, like we were able to write down the double inclusive cross-section for the case of PA, which were written as uncorrelated contribution, which is like the completely classical contribution, where the two gluons that you produce are not talking to each other. Then it's ordered 1 over NC square minus 1. You have a contribution that comes from the Bose enhancement of the projectile gluons and HBT gluons. And in the NC square corrections to that, you get Bose enhancement of the target gluons and NC corrections, NC suppressed corrections to the Bose enhancement of the projectile gluons. Before I go into multi-gluon production, let me also make an advertisement of a paper that we wrote recently. By recently, I mean, okay, it has been already 1 year. But we were also able to calculate the correlations between the total multiplicity and V2 from CGC. And for that, basically what we had to do was to define the operator, the observable for this correlation, as starting from the triple gluon cross-section or spectrum, you integrate over one of the gluons, and then you do the azimuthal integration over the angles of the remaining two, which then has to be normalized as the same quantity for the double inclusive cross-section and the total multiplicity, where you only integrate when you calculate the spectrum of a single gluon and then integrate over this spectrum. The only difference here, we were also integrating over the transverse momenta of the gluons that are produced with some transverse size beams. So this here delta is the size of the transverse beam, and we were able to identify what kind of contribution or what kind of physical effects were taken into account when we have non-overlapping beams or when we have overlapping beams. beams. In the case of non-overlapping beams, for example, there's only the Bose enhancement contribution that appears. But okay, when you start having the beams like overlapping, then HPT starts contributing, and in the case of fully overlapping beams, both Bose enhancement and the HPT contributions are important. So now let me continue with, after all these basics, let me now continue with the multi-particle correlation. So why do we want to calculate that? Because okay, like the first thing is that, of course, like the same as like two-gluon production, is we want to study the collective behavior in small size systems, PPTA, from the initial state. But we also would like to understand and explore the properties of four-particle correlations from the CGC. Now, what we see here is a plot that I took from CMS, where we have both PP and PLED collisions at different energies, 13, 7, and 5, and now for PLED it's at 5 TeV. So this is the four-particle cumulant as a function of the multiplicity. So what we see here is that okay, like the four-particle cumulant is negative for high multiplicity events, and it becomes positive for low multiplicity events. There are also previous CGC calculations that studied four-particle correlations. So one of them is from Adrian, Larian, and Bloody, where they look at the dilute regime. So like this is like the weak field limit of the PA collisions, and they were able to see that okay, like there's the four-particle cumulus that they calculated was positive. On the other hand, there's another paper by Kevin, Mark, and Raju, where they calculated negative four-particle cumulus in the dilute dense regime, but they were only taking into account the quarks, so there were no gluons in their calculation in order to simplify this full calculation. And you will see in a second why it's important to simplify these calculations. So let me first remind you that the technical aspects. What do we have? How do we calculate these things? Yeah.
So on this four-particle correlation, can you explain me why would people expect this particular observable to sensitive on the initial state stuff?
This is still a small size system. It's PP and PLED.
Yes, but you know, you can have jets, you can have more interactions, and a lot of other things.
Yeah, but okay, our motivation is to understand it from the CGC. And okay, let me also, okay, thank you for the question, and let me also emphasize something as a disclaimer. Here, okay, I have no motivation or no intention to describe data. I just would like to understand, okay, what we would get from a CGC calculation. I'm not trying to fit the data or anything, okay? I would just like to understand this. Okay, so for the case of multi-particle correlations, for any number of gluons, let's say, we have the dilute projectile, which is defined by random color charge density, as I was saying before. The target is dense, so it's defined in terms of the classical color fields, A minus. There is the icon of interaction between the projectile and the target. It's given by a Wilson line. Obviously, it's okay. Like here, we wrote it as the Fourier transform of this guy, and the gluon emission before or after the interaction is given by the Lipatov vertex, which is what I have written here. So, okay, we would like to write down a generic expression for multi-gluon production at leading order, which means that, okay, we're neglecting multiple emissions by a single color charge density. In other words, we are only taking into account, if I'm looking at like two-gluon production, it means that, okay, each of these gluons has to be emitted from a separate source. We are not taking into account anything like a single source emitting two gluons, or two sources are emitting gluons, but then okay, these gluons merge together, and then it gives a single gluon in the cross section. So we are completely discarding these kind of corrections. We are only looking at the generalized Glasma-Graph type of calculations. So in that case, I can write the n gluon spectrum as a product of single gluon spectrums. So for the multi-gluon, okay, in that case I can, okay, so what I have to do is I have to integrate over each of the momentum transfer from the target, Q here, Q2i minus 1 and Q2i. Of course, this is going to happen for each one of the amplitude. Then I have to average over projectile color sources. And then I also have to average over the target fields, which is what I call as the reduced matrix element, reduced scattering matrix M. This matrix M is given in terms of the Lipatov vertex, so it takes into account both of the emission of gluon before or after the interaction. It takes into account multiple scattering because of the Wilson line that I have introduced here. And here epsilon is the gluon polarization vector. So what I have to do is I have to take these guys and multiply it with n times, and then I have to perform averaging over the projectile separately, and then averaging over the target separately. And on top of that, I have to integrate over each of the momentum transfer that I see in the process. So,
Tolga, excuse me.
Yeah.
Can you go to, just since you are here on the technical side? So this, can you explain a bit about this amplitude? So this Lipatov vertex kind of appears if we assume that there is one exchange with the medium, with one gluon exchange with the medium, but then you have this Wilson line there.
No, okay, so let me interrupt you there. Okay, it's not just that. Okay, so so in principle, okay, there are two different ways of writing this. You can take into account the emission of the gluon before or after the interaction, either by writing it as in terms of this Lipatov vertex, or you can just have a Weisser-Williams field, which is like Ki over K squared. But then, okay, different Fourier transform of the Wilson line. So you basically take into account all possible interactions. So it corresponds to either setting your shock wave or your interaction to either here or here. So in one case, okay, you have the gluon that's already emitted, and in the other case, you have okay, your projectile is scattered or interacts with the target before it emits the gluon. So the gluon is emitted after the interaction with the target.
Oh, okay.
Okay.
Mm-hmm. It's kind of Q is the last. Sorry, is it a naive question? Is Q the last scattering then, or something like that?
No. Q. Okay, so let me go back. It's much nicely explained here. So Q is the momentum transfer from the target. Okay. Yes. What you have in the projectile is K minus Q. So this is the momentum of your color charge density. And then you are basically producing a gluon with momentum K.
Mm-hmm.
Okay.
I see.
All right.
So what is covered? So the Wilson line is basically following this emitted gluon.
So the Wilson line is taking into account both the emission of the gluon and also the scattering of your color charge on the target without the emission, and then it emits a gluon. So this subtraction term here, K minus Q, basically corresponds to the case where your gluon is emitted before the interaction, and this Ki over K squared is actually the case when your gluon is emitted after the interaction. So one of them is coming with positive, and the other one is coming with the negative side.
Okay.
Okay. And this is actually this is actually the standard Lipatov vertex, but written only in the transverse coordinates. So it literally goes to that, except the fact that, okay, like, of course, like when we're writing, because it's only including like the transverse momenta and transverse index, it looks a bit different from the standard definition of the Lipatov vertices. Okay, so then, okay, it is kind of obvious what we have to do, but the question is, okay, how we can do it, right? Okay, so the first thing that we should understand is how we can do the projectile averaging. So for that, okay, we're assuming a Gaussian distribution, which is the standard MV model type of treatment. So for any pair, so we have like two n pairs of color charge density in the amplitude and in the complex conjugate amplitude. So we basically calculate these guys like through the V theorem, which means, okay, we pick pairwise correlators, and then we take the product of all possible pairwise contraction, and then we sum over all these possibilities. So, but then, okay, on top of that, we also use a Gaussian profile for the 2-point correlation instead of a drag delta function. So in principle, okay, in the standard MV, you basically take this as a delta function, delta of Ki minus Qi plus delta plus Kj minus Qj. But here we are taking it as a Gaussian profile, this function mu, and this function mu has this transverse area, the information about the transverse area of the projectile. Then the next thing is the target averaging. So how can we deal with the target averaging? In principle, okay, like we will have multiples. It's not going to be only like double dipole or quadrupole, but okay, like if you look at like 3 particle correlations, we will have sextupoles, triple dipoles, dipole quadrupole terms. If you go for 4 gluons, that's going to be like octupoles, double quadrupoles, and okay, like things get very complicated easily. However, as I said, we're kind of using the domain model. So in other words, okay, like let me again remind you what is this thing. So in this case, again, we are assuming that, okay, like in the target, our target is composed of chromoelectric fields with each domain as the length of 1 over QS, and the correlation between the particles originating from scattering through the same domain. So it basically tells us that the correlator can be decomposed. Okay, we can write down this and we can decompose it into smaller pieces, but at least 2 of the legs should be sitting in the same domain pairwise. So in other words, we can have like this kind of contribution, these 3 kind of contributions, but we don't have this fourth kind of contribution where all the legs are sitting at the same domain. And this is because of the area enhancement argument. It basically tells us that, okay, this kind of configurations in which more than 2 legs are sitting in the same domain are suppressed by the phase space area after the integration. And this is, let me again come back to this expression, and let me even try to make it simpler to understand. So here we have 4 coordinates. Our Wilson lines are sitting in 4 different coordinates, y1, y2, y3, and y4. So no matter what, okay, we have to integrate over these guys. So, okay, in order to integrate over these 4 guys, okay, like the main contribution, the leading contribution will come from when all these guys are far away from each other in the transverse plane. But then, okay, like if you have all these four coordinates like completely far away from each other, then you cannot form singlet pairs, and this is the idea. So you need to have like color singlet states after doing the averaging over the target. So okay, if this is the case, it means okay, like pairwise, those 2 coordinates, any 2 coordinates should be close to each other, but then these pairs have to be far away from each other in order to cover as much as transverse area possible when we are doing the integration. So this is the idea of the area enhancement argument, which was introduced by Alex and Amir in 2017. But okay, this basically also corresponds to, or it's analog to, assuming Wilson lines following a Gaussian distribution. So it means that okay, we can also use the Wick theorem as we did in in the case of projectile averaging. It means that, okay, I have to look at pairwise Wilson lines, look at all possible contributions, and then sum over all different kind of contributions. On top of that, okay, we're again assuming color neutralization in each domain, which means, okay, any of UU dagger has to be written as a trace UU dagger with the appropriate delta functions for the colors, and of course the normalization. And for the dipole function, we're basically using the GBW model. So it's again a Gaussian distribution with respect to QS square. Okay, so very good. It looks like, okay, we have an argument that we can use, but then the question is, okay, like how good it is when compared to when compared to the actual MV model kind of calculation. So in this paper, we already calculated a double dipole function in the fundamental representation by using the area enhancement argument, which is given here. And in this paper, Fabio, Cyril, and Bin, they calculated the double dipole function in fundamental representation using the MV model. So here you see that, okay, like even in the simplified MV model, when you're neglecting the logarithmic dependence of the QS on the transverse size or the dipole size, this function here that you see here is way too complicated, because you have not only the definition of F is complicated, but on top of that, okay, each of these deltas that are appearing everywhere in the exponents and in the numerator are nonlinear functions of this function F. So, okay, compared to this area enhancement argument, okay, like this MV model looks way too complicated. But then we decided to look at it numerically. So we calculated the expectation value of the double dipole with an MV model and look at the ratio of what we get from the area enhancement argument. And we plotted as a function of BP times QS squared, and remember BP was appearing in the MV model, and on top of that, okay, BP times QS squared is roughly like the number of domains that will appear in the overlapping area during the interaction. So what we really see here is that for a double dipole, using MV model or area enhancement argument it really doesn't change anything as long as our overlapping area is large enough, like the ratio goes to 1, as you see. So which one would you like to use? Okay, this simple expression or this very complicated one? This one is much easier to handle, and we kind of have an idea of what's going on as the physics behind this whole calculation in that case. Now, life is not that simple. This was what I have shown you was the double dipole, and now we can also look at the quadrupole. And in the case of quadrupole, okay, like we have again two contributions from the area enhancement argument, but we also have like this complicated expression for the quadrupole in the MV model. And in that case, life is much more complicated. So this is the ratio of the quadrupole calculated in MV model to the case where quadrupole is calculated in the area enhancement argument. And this ratio is plotted as a function of the number of domains, again, BP times QS squared. And we see that, okay, like it's not as smooth as double dipole, but in the worst case, like the difference between the area enhancement argument and the MV model is like up to 25%, which is okay, which is big, but still acceptable, I would say. Okay, so now we kind of know. Okay,
so guys, excuse me, small question.
Mm-hmm.
For a quadrupole, as you write there, in principle, we know how it should. In the large NC limit, we know we can also use the large NC limit to describe this. So I don't know exactly what this integral there means, but it probably means integral of all the transverse positions. But In principle, if you
Yes.
fix the transverse positions, you know, in principle, that at the large NC limit, this quadrupole is basically your first term there, plus a term which is NC suppressed that describes kind of a connection between two of the lines, and then it flips, and then it.
But okay, like is this quadrupole that you're talking about, is it a fundamental one or an adjoint one?
Well, if you want to describe it in terms of a fundamental one, for okay, but it also works for an adjoint one, right? In a large NC limit, it's basically the same.
Okay, let me go back and let me show you. Okay, like so here you see that, okay, like this expression that I have written here is the quadrupole. This is an adjoint quadrupole, which is written in terms of this area enhancement argument. So I have like two different terms that give me the same order in NC, two different contributions, and there's an NC suppressed correction to that. So
yeah, I mean it's so your Wilson lines, they live basically from minus infinity plus infinity, right?
yes.
But basically, the large NC limit, so you can show that the quadrupole basically describes it basically reduces to kind of dipole dynamics, but basically you start out with some. This is a result from Fabio, I guess, and Bowen and the old paper. So you have basically two dipoles, a pair of dipoles that basically is in the wrong color state, and then there's a transition matrix, and it flips over to the final state, right? So how is that related to this? Is that what they used in this MV model, or is that something related to what you're doing?
Okay, that I'm not exactly sure how they calculate this quadrupole function in the MV model. I honestly, okay, I don't know the details how they have calculated it, but okay, like it might be completely related, because okay, the whole idea is to like write something in terms of dipoles, and then some kind of correction to that, where all these F's and deltas and blah blah blah, they're okay here, they're all coordinated.
Yeah, so like for instance, your number of colors counting here is not really completely good, right? Because on the left hand side you have one trace, so that will give you one power.
Sure.
And on the right hand side you have two traces, right?
No, of course you're right, because okay, like this is not an equality. I just wrote it like as
okay, like a sketch.
It's a sketch, because okay, like here for example you see that okay, this is also not exactly the same story. I just wanted to write it like this in order to show that okay, in the case of double dipole you have explicit 1 over NC square correction, and in the case of quadrupole you have like the two terms that you're writing is actually coming with the same color of with the same NC counting, even though okay, in one case you have 1 over NC squared, because okay, it's a single trace, and in the other one okay, you have double trace, of course.
Yeah, I'm mentioning this actually because we have an expert in the room. So Johannes is Johannes is just to make a connection to. So Johannes worked a bit has worked quite a lot on this quadrupole function. So we managed to, in fact, solve for any correlator. In principle, we were working in the fundamental approximation, but we have a method to kind of extend it to higher order. Color representations or something, but in principle, it could be an interesting point to look at some point. Like
I completely agree.
Consistent NC counting, let's say.
And especially okay, like what you're saying is really good comment, because okay, we were also discussing about with Cyril and how to improve this area enhancement. Okay, I will definitely look at this paper.
Okay, great.
Thanks a lot. But okay, so now let me continue. So let's assume that okay, like I accept the fact that okay, like even though there is okay, like 25% of error for the quadrupole case, let's assume that okay, I'm okay with that, and I would like to continue. So if I want to continue, there's another problem that I have to understand or I have to fix, which is related with dealing with the infrared divergences. Because like anything that will be appearing in my m square, the amplitude square, I will always have square of the Lipatov vertices. And these guys have infrared divergences in the collinear limit. In other words, when Q is similar to the values of K, then there is a problem. How do we solve this problem? Okay, like the one way of doing it is introducing a cutoff and using this explicit expression for the Lipatovs. But another way, which we find is much cheaper to do, is to use a Gaussian regularization in the collinear limit. In other words, we introduce, so instead of using this expression for the Lipatovs, we're basically using an exponential of function of k minus q1 and k minus q2 with a regulator of xi, or xi square. So in this limit, indeed, in this collinear limit, we can actually relate our approach to the Wigner function approach that was introduced by Lapie and friends later on, where they say that, okay, if they want to calculate a single gluon spectrum, they can simply write down the expression in such a way that, okay, it will be like the Wilson line structure that will come from the target, and anything that will be happening with including the Lipatov vertex and the description of it in the projectile wave function is given in terms of this Wigner function here. Now, of course, at this point you can say, okay, look, this is an approximation. It is true. It is not written in like by using the first principles or anything. However, it has advantages. First of all, it's trivial to integrate because, okay, it's a Gaussian. And second is that, okay, if you write our square of the Lipatov vertices in terms of this exponent as a Gaussian, then we can relate the Wigner function approach, but in our case, it also includes the quantum correlations in the projectile wave function. In other words, we're basically taking into account the Bose enhancement of the projectile wave functions. However, okay, there are also disadvantages, and these disadvantages are that, okay, first of all, it's not fundamental, as I said. Second, it has a limited kinematical coverage. It's only valid for k square around qs square. And it's also admittedly not fully consistent, because I started this whole discussion saying that, okay, I would like to calculate something like 4 gluons or gluon correlations, multi-gluon correlations at mid-rapidity. But the collinear limit is suitable for forward rapidity. But in any case, let me continue. One thing is that, okay, like again, I would like to emphasize this. In principle, okay, all these calculations that are done with the Wigner function are assuming the factorized Wigner functions for the two particles that are produced. In our case, we have the uncorrelated one or the factorized one, but we also have the contribution that will include the Bose enhancement of the projectile gluons.
Tolga?
Yes.
So what is Xi? Can you tell us? So
okay, this Xi is basically just a regulator. You see.
Right. So well, what does it mean? What kind of regulation? Because in principle, this Lipatov vertex
it's regulating the infrared in k minus q. So you see the exponent that I'm writing is k minus q plus k minus q1 plus k minus q2 squared. And okay, I'm regulating it with xi square. So if I keep this xi square finite, okay, so this is kind of the Gaussian regularization that we introduce in order to get rid of this.
You see, I mean, this is again an interesting point. So typically when we do jet quenching and we do these similar diagrams, we assume, of course, that the emission has to, for instance, we are interested in the induced emissions of gluons, which appear again with this Lipatov vertex, and but they, of course, to be induced, you have to happen inside of the medium. So you will have the regulator there is basically a formation time similar to the length of the medium, basically.
That is true, but okay, again, I would like to remind you that, okay, this is full Eichel, which means that, okay, for me, everything that's happening is happening like in a shock wave. So there's no finite width of the medium.
Exactly. So you're missing this kind of physics
Yeah.
But of course, if you look at the Lipado vortex, I mean, your interaction with the target takes place. So I'm just wondering about these, as you were discussing. So the Lipado vortex, you have emission before you hit the target, after you hit the target, and then from the gluon that hits the target, right? So from the gluon from the target. So there is one of them at least that you radiate the gluon inside, isn't it, or not?
No. So there's nothing inside. So it's basically either the gluon is either emitted before or after the interaction with the target, because there's no finite width. So this is everything that I'm doing here is like at iconal accuracy. So there's no subiconal stuff. But okay, I also have to say that, okay, like hopefully before the end of the year we will put another paper which is done for finite width.
Okay, but in the Lipado vortex there's this third diagram where you interact.
That is, yes, that is only the, okay, that is only,
so you only have the two.
That is only the case, like this third diagram only appears if you have a finite width, because it's like basically of the gluon inside the target.
Yeah.
And
okay. Exactly.
Because of the shockwave approximation that I'm using here, that the third contribution is not appearing.
I see. So yeah. Okay. Thank you.
Okay. All right. So, okay, what I was saying. Okay. So, okay, like this is just a summary of what I have been saying. So, in principle, okay, we can calculate any number of gluons by using this formula that I have written here, with the assumptions that, okay, we are using MV model for computing the projectile averages, which means, okay, we're using big theorem, which means, okay, like from the projectile averaging, we're getting 2n-1 double factorial terms. From the target averaging, we're using area enhancement argument, which also corresponds to like a Gaussian distribution, which also means that, okay, I can use the big theorem, and it also tells me that, okay, from that I will also get 2n-1 double factorial terms, and I'm using Gaussian form for the product of two Lipado vertices that kind of mimics the Wigner function approach. Since the integrand are Gaussian, these are, okay, we can do these integrals in a trivial manner. However, you also need to understand that because of the fact that, okay, you're producing so many terms, which is 2n-1 double factorial squared. So for two gluon production, you need to calculate 9 diagrams or 9 terms. For 3 gluon production, you need to calculate 225 of them. For 4 gluon production, you need to calculate 11,025 terms. So it is increasing very rapidly, and it's going crazy very easily. So the number of these terms, we can reduce it drastically by realizing the symmetries between the momenta at all orders in NC. And okay, we have like introduced this diagrammatic method in this paper. But let me continue, because okay, it looks like I'm really running out of time. I already ran out of time, but okay, I don't have too much slides left. So let me just tell you, even though I'm pretty sure you guys know these things, but okay, like, so what we would like to do is we would like to write down the cumulants. So 2-particle cumulant and 4-particle cumulants, which are defined in this way. We need to do the event averaging for each of these phases, which are defined in this way. And of course, at the end, we would like to look at also the azimuthal harmonics. So for 2-particle and 4-particle correlations, which are defined in terms of the cumulants as the root or 1/4. So of course, like we have the analogous expressions for the differential cumulants, which are dependent on PT. So, okay, for the double inclusive gluon production, we have the analytical results that are all written in terms of hypergeometric functions. Again, I would like to emphasize one more time that I'm not trying to explain any data, but like the numerical values that we got, most of them lie in the bulk of the experimental data. So the first diagram, the first plot that you see here is like two particle correlations. So it's like second and fourth harmonics for two particles as a function of this psi square over QS square. And again, let me remind you, this psi square was the cutoff that we introduced in the square of the Lipatov in the Gaussian form. So BP times QS square corresponds to roughly the number of domains that interacts during that you get in the interaction. So what we see here is that, okay, like for small, if I take this ratio to smaller values, okay, the correlations are increasing rapidly, which is what is expected, because, okay, like if you take psi to be like your ratio to be smaller and smaller, of course, like you're going to a place where you will feel more of the divergence. But then, okay, for larger values, okay, they're not, like the change is kind of small. And for V2, again, for fixed value of psi square over QS square, for this ratio, which is 1/4, the number of the V2, so again, V2, V4, for two particle cumulants as a function of the number of domains is showing a similar behavior, which means, okay, like for smaller values of domain, the number of domains in the interaction, the correlations are increasing, which is basically what one expects, because, okay, if you have less number of domains, then the probability of having scattering through the similar domain increases, thus the correlations that you're looking for is increasing. And finally, I would like to show you that, okay, like V2, V4, V6 for two particle correlations for the values of QS square 2 GeV, BP6, and psi square 0.5 as a function of PT. Again, it shows this beautiful behavior, and the values roughly lie in the bulk of the experimental data. The important part is the
Excuse me, Tolga.
Yeah.
I have to go to an institute meeting. We are starting now with the organization of the institute. So I'm the group leader here in our theory group. So I will have to go. I'm sorry for that.
No problem.
But now
it's
some discussion. Yeah, but I'll catch up with you later. Maybe we can chat also some other time. And thanks a lot for speaking to us. Yeah.
Sure, no problem. Bye.
Yeah. See you later, guys. Bye.
Okay, so let me just wrap it up. Okay, so for us, what was important was to see the four inclusive gluon production, and for us, it's also important to see that, okay, like the four particle cumulants that we calculated are negative, which is what we see in the first plot as a function of QS square. Okay, both C2 and C4, like the second and the fourth cumulant of four particles are negative, which gives us the positive values of azimuthal harmonics. So it's good. So it's well-defined azimuthal harmonics. Again, numerical values lie in the bulk of the experimental data. And here we also see a similar behavior for the differential cumulants, which are a function of PT. And finally, okay, we also have the azimuthal harmonics as a function of PT for V2 and V4 for two particle and four particle cumulants, and we see that, okay, it is behaving in a very nice way as a function of PT. Now, okay, finally, let me just summarize. So we have introduced a new approach for computing multi-gluon production and solve up to four-gluon production. We have obtained a negative four-particle cumulants in PA collisions, which is well-defined, which tells us that, okay, like the azimuthal harmonics are well-defined. We have introduced a new way to include Bose enhancement correlations into multi-particle Wigner function. And I would like to emphasize this: without including these correlations in the projectile, one gets positive four particle cumulants, which is bad. And I also would like to say that, okay, our approach should be improved by including different things. One of them is including the contributions in which more than one gluon is emitted by a single source. So this is like a contribution to the projectile wave function. Then we also have to go beyond the area enhancement argument and try to include the 4 Wilson lines sitting in the same domain, and at least try to see what would be the numerical value if we include that. And also we need to use the true expressions for the Lipat of vertices instead of using this Gaussian. So for future, we also would like to study the dilute limit of our calculation to see whether C24 is negative, and can we explain from first principles the change of sign of C24 from small to large multiplicity events. Well, okay, so this is all what I wanted to say. Thank you very much, and I'm really sorry it took me more than expected.